Okay, so welcome back, guys. So today is April 19th. So today we released the module number 11, test for contingency tables. And your mission is due today, mission number 8. So this will be the second to last module that you'll be learning. We'll finish that up with a course review on May 3rd, but this week the test for contingency table, and next week the inferences for correlation and simple linear regression will be the remainder of the material that we'll be teaching you this semester. So at this point, since the final project deadline is coming up in just about 2 weeks, it's a good idea to start thinking about working on that, since it'll be due in 2 weeks from now. So it's a good idea to start taking a look at what data set you'd like to work on, what your research questions are, and start thinking about what kind of statistical analyses you'd like to perform on that data set. So just to start off, I want to see if anyone had any questions. I'm happy to answer any questions, or we can go over some of the material for the course, or we can discuss the final project, whatever you guys would prefer. Do you have any questions at this point? So we've uploaded some sample final projects as well, along with some guidelines that you can take a look at for some guidance on how to format your final paper. And Michael just had a question regarding the alpha level. So why don't we pull up one of the lectures and go over that. So let's take a look at module number 8, the sampling distribution, so that we can start talking about the alpha value and what the alpha value represents. So this is the sampling distribution module. And the basics of what this module was on was it built upon the last module of the basics of sampling, and this introduced us to the central limit theorem, to confidence intervals, and to the basics of hypothesis testing. So in this module, we taught you about the central limit theorem, which says that so long as we have a large sample size, we can assume normality due to the central limit theorem. And we can just skip ahead. Then we spoke about about confidence intervals and point estimates. when we talked about hypothesis testing. So we introduced the concept of alpha here. This is what the definition of alpha is. So what alpha actually represents is the probability of having a type 1 error. And a type 1 error is when you reject the null hypothesis when it's in fact true. So it's like a false alarm or a false positive. So it's what's known as a false positive error. So that's going to be the alpha is representative of the probability of a type 1 error occurring, which is to say you will reject the null hypothesis when it's in fact true, which will be the probability of making a false positive error. So the alpha value, that's actually what it is, the pure definition of it. And when we talk about confidence levels or confidence intervals, our level of confidence will be 100% minus our alpha. So if we have a 5% alpha value, which is to say there's a 5% chance of having a type 1 error occurring, then we will have a 95% confidence level for that particular test. If we have a 10% alpha value, that means that we'll have a 90% confidence level. So they are inversely related, the alpha value and the confidence level. So this is how we first described the alpha values. And then just going back, taking a look at how that affects hypothesis testing is in the following modules, we introduced the first type of hypothesis test, the test for means. So we can take a look at how we use the alpha values in the context of a hypothesis test. So this is the test for means, which we said, which introduced us to the two types of tests that we have to test means within samples. We can use either a z-test for normally distributed data, or we can use a t-test, which specifically was designed to handle small sample sizes, but can also be used with any type of sample. So in this case, we see here that the alpha is usually 0.05, but it can change based on the test you're running and your own level of confidence that's required. And based on our given alpha, it will give us a corresponding critical value for our test. So for a two-tailed hypothesis test, for the normal distribution, for instance, you will use what's called the Z alpha over 2 critical value in order to run your hypothesis test. So the way that the hypothesis test will work is this is a 95% two-tailed representation of the normal distribution. So we are looking here at a 95% confidence level of the normal distribution as represented here with these two Z critical values of a positive Z-score of 1.96 and a negative z-score on the left-handed side of negative 1.96. And this will have that alpha value of 0.05 distributed evenly on the two tails, which are represented in the light blue and the brown region. So as you can see, on the right-handed side, this is 2.5%. So half of that alpha is on the right-hand side. And on the left-hand side, you have the other 2.5%, which is shaded here in brown. So together, if you add the two, that will give you your 5% alpha value. And then if you take the inverse, that's everything here shaded in green, this is representative of that 95% confidence level. So when we're running a hypothesis test, we're coming up with a test statistic for the given test, and we're seeing how it compares to our critical values. So that is to say, if your test statistic falls within the screen region, which is in between the two critical values, you do not reject the null hypothesis. That's not a significant result. However, if your test statistic is more extreme, that is to say that if it's greater than 1.96 or less than negative 1.96, that is a significant result, and you would reject your null hypothesis. And you would conclude with the alternate hypothesis. So that's how we understand the alpha value in the context of hypothesis tests. So the alpha, what it represents is it represents the probability of making a type 1 error, which is a false positive. And we use it both in building confidence intervals and also in running hypothesis tests to make our determination of conclusions, because the alpha value will determine what our particular critical values will be. So depending on what test you're running, whether it's a z-test or a t-test, first you're going to have a different distribution. The second factor is you're going to look at your given alpha and whether you're running a one-sided or a two-sided test to come up with your particular critical values for which you're going to compare to your test statistic. And the test statistic compared to the critical value will lead your conclusion of what to conclude for that hypothesis test. Does that make sense, Michael? So a conclusion based on the normal distribution. So only dealing with a two-sided z distribution will use the critical values of negative 1.96 and positive 1.96. So the way that you can come up with these critical values is either A, you can use a statistical software like R, or B, you can use a normal distribution table. So I can show you how a normal distribution table looks. So this is how a table of normal distribution values looks like. So the way that this works is have your alpha values. So first you have your Z. Hold on one second. I'm going to show you on both ways on how to do it using R. So I'm just going to load up R, and I'm also going to show you how to read a normal distribution table. So I'm just loading up my R package. So I just pulled up my my RStudio, and I just loaded the Mosaic package into R. And I was just looking at the data set that we worked on for the module number 6. So here, if you remember, we were dealing with the Iowa census data, which looked at gender, age, years of education, income, and location in the state of Iowa. So here, what we can do is we can look at different different z-scores to find the percentiles based on the normal distribution. So we can use the QDIST formula. to find an illustrated quantile calculation from a given distribution. So in this example, just for a normal distribution, we can look at what the z-score would be for the 90th percentile, right? So if we run this command, looking at the normal distribution with the 90th percentile, this will show us the given z-score for that. So it will show us the given z-score for that percentile. So when we're dealing with an alpha value of 0.05, we can actually we'd be looking at the 5th percentile. Sorry, we'll be looking at the 2.5 percentile on the left and the 97.5 percentile on the right-hand side. So we can look at 0.2025 and 97.5. So we can look here. This is representative of the 95th, a confidence level of 95th percentile for a two-sided z-test with a normal distribution. So because there is an alpha value of 5%, which is divided between the two tells, represented in the blue and the red here, the corresponding z statistic values are negative 1.96 and positive 1.96. So if we were curious about what the given statistics were for an alpha value of 10%, we would have to find the corresponding z statistics. So the way we can do that is the inverse command, which is the qdist function. So we could do qdist distribution equals normal. And for the p, since we would be looking for an alpha of 10%, that would mean that there's 5% on either side, right? So that means on the left-hand side, we'd be looking at the 5th percentile, and on the right-handed side, it would mean that we would have the 95th percentile, and that would encompass a 90% confidence level between those two critical values. So for here, for p, I will be putting in 0.05. And this shows us that the corresponding critical value on the left-handed side is negative 1.645. So correspondingly, if I were to put the p as 0.95, we expect it to result in positive 1.65, which it does. Correspondingly, if we looked at those two, we would find that there's a 90% confidence level here, illustrated in this green region, and our two critical values for a alpha of 10% using a two-sided test will be negative 1.645 on the left-handed side And on the right-hand side, we would have a positive 1.645. So those are the representative Z critical values for an alpha of 10%. This is for the normal distribution. So with the t distribution, there is going to be different critical values depending on your degrees of freedom, because the point of the t distribution is it will adjust with your sample size, because the point of it is to be able to handle and adjust for small sample sizes. So we can play around with this with any level of significance that we'd like to see how those critical values will change. But the whole point of doing this exercise is to use it in the context of a hypothesis test, because this will show us the regions of rejection for our hypothesis test. So for this given example, we can use this illustration to run a two-sided hypothesis test for the normal distribution using a 10% confidence, a 10% alpha, so 90% confidence. So you can see here where it says B, this green region, this is the 90%. And on each side, in the red and the blue, those are 5% each. If you add those two together, that will come up with the 10%. So likewise, you can actually do what's called a one-sided test by just looking at one side of the distribution versus the other. If you were to do a one-sided test, that critical value will change as well. So we could use an alpha of 0.05 and just look at so for instance, if we were looking at a one-sided test on the right-handed side for a 95% confidence level, the Z critical value that we would use is 1.645. But if we're using a two-sided test with the same alpha value, that would be 1.96. And the reason is because for this one-sided test, you have that full alpha value of 5% on the right-handed side. It's no longer split amongst those two tails anymore. So that's why your critical value will change based on that. Because you're not looking at an alpha divided by 2, you're just looking at the critical value of Z alpha here. Does that make sense? Does that help? Right? Does that help clarify that? So, the main takeaways for the alpha value is to know that the level of confidence and your alpha value is going to have an inverse relationship. So if we have an alpha of 5%, we're dealing with a 95% confidence level. But that being said, when you're dealing in the context of a hypothesis test, you have to first understand whether you're dealing with a one-sided test or a two-sided test. If it's a two-sided test, that alpha, that region of that critical region of rejection is going to be split amongst the two tails. If it's one-sided, it won't be. It's only going to be on one side of the distribution. And then if you're dealing with, let's say, the normal distribution, then you can find the representative critical values for your given alpha value. So typically, since we're using a 5% alpha, and probably they're going to be using a one or a two-sided test, you're going to typically be dealing with the z-scores of plus minus 1.96 for a two-sided test. Or for a one-sided test, you'll be using 1.645 for an alpha value of 5%. If you're dealing with a two-sided test at a 10% alpha value, you'll also use the 1.645 z-score. Because in that case, now you're dealing with two tails, each having a 5% alpha on each to add up to a 10% alpha. Yeah, so when we're talking about a p-value is the probability of getting any random variable more extreme than our test statistic. So we can use a given example here. I'm just going to switch the data set so we can take a look at another example. So I'm going to load in the employed ACS data set. And the respective PSET code. And then I'm going to load that into R. And we can go back to R once it's loaded in. We can look at this employed ACS data set. So this is dealing with the data as you see here. It's similar demographical data as that last data set we were looking at. And here we can look at the respective R code. So we can go through some of this code together. So first, the mission asked us to take a look at some summary statistics and look at the average income and the median income. So we can run this code. So we see here the average income was about 41,300. If we take a look at the median income, we see that the median income is 28,900. So as you can see here, the mean is larger than the median value. So it shows that there's probably some skewness in the data. So the next question says, based on previous research, a prominent economist thinks the average income in the population is 35,000. Conduct a one-sample, two-sided t-test with a null hypothesis that the average income in the population is 35,000. And what do you conclude based on the alpha criterion level of 0.05? So we can run a t-test for this. So the t-test is a hypothesis test, and the hypothesis test will be testing whether the null hypothesis of the average income in this population is 35,000, right? So here we actually just found that the mean is 41,300, but the median is lower. It's actually 28.9. So our question is whether, using a t-test, whether the population average income is 35,000 or not, and we're using an alpha value of 0.05. So this will be a two-sided t-test using the income data in this data set, and with a mu equal to 35. We could also add in our confidence interval. And the way we would do that is by using the confidence level command. So we'll use this t-test formula, telling R to look at the income variable in the employed ACS data set with a null hypothesis mean of 35,000. And we can put in confidence interval. Level equals 0.95. And we can run this command. Oops, sorry. Conf.level. Okay. Sorry about that. So this is the result of our t-test. So here we can see that we got a p-value of 0.01847, right? So in order to find out if this is a significant p-value or not, we have to compare the p-value with our given alpha value. Here we said we're running a test with an alpha value of 0.05. So what we're looking at is whether this p-value is more extreme than the alpha value or not. And because the p-value of 0.0847 is less than our alpha value of 0.05, we will reject the null hypothesis. That's a significant result. And it shows us that we're 95% confident that the true population income is not 35,000. So it actually built out a 95% confidence interval for us as well, showing that the lower bound is 36,000 and the upper bound is 46,500. And since 35,000 is not contained by that interval, we reject the null hypothesis and conclude with the alternate. But we can see here, if we actually use a 90% confidence interval, we can actually see how that changes our results here. So if we use a 90% confidence interval, you can see that we still get the same result. And the confidence interval actually now goes from 37,000 to 45.7 thousand. But now let's take a look at what if we make it a more stringent confidence level. What if we use a 99% confidence interval? How will that affect things? So let's take a look at plotting this now. So the question asks us to plot the critical values using a t-distribution model for the sampling distribution and ask us what is the probability of obtaining a more extreme t-value. So this is, in effect, what's looking at. We're taking this test statistic of 2.367, and we're going to look at that with this given t-distribution with a degrees of freedom of 342. And taking a look at the probability of having a more extreme value than that test statistic. So we can run this code. And this actually shows us here, it shows us the probability of getting a more extreme value on either side. And this is a two-tailed test, right? So it shows us here that the p-value for a t of 2.3674, the probability of getting a value more extreme than that on each side will be 0.009, or about 0.9%. But because that's only dealing with one side, we actually have to multiply it by 2 in order to come up with our p-value, because that's only showing us on one side, and we're dealing with a two-sided test here, so we have to multiply that particular probability by 2. So in order to come up with the answer to this question, the probability of obtaining a more extreme t-value, either positive or negative than the one we actually obtained, we would take this 0.009, multiply it by 2, and come up with our p-value of 0.01847. And because we're dealing with a t-distribution with degrees of freedom of equal to 342, we can find what the critical values of a 95% confidence interval would be in order to find whether we would reject or not reject or null hypothesis. So the way we can do that is by taking a look at the Q-dist of a t-distribution with degrees of freedom equal to 342, and combining on each side. On the left-handed side, we would have 0.025, and on the right-hand side, we would have 97.5. Sorry, not Q, but P is equal to. So this shows us that the critical values for a t-distribution for 95th percentile will be plus minus 1.96. So what we can do now is we can look at this distribution. So what we're looking at here is in green, this is representative of the 95% confidence level for this given t-distribution with degrees of freedom of 342. What we're looking at in this blue region, so just imagine this whole region is shaded blue. This is representative of the blue plus the purple is an alpha of 2.5% on each side. And we can see that here because this is the blue region of 0.016 plus the purple region of 0.009. So if we add those two numbers together, that will come up with a 2.5% for this entire tail here, the blue and the purple. And on the left-handed side, it's the same. This is also representative of 2.5%. So then what we're looking for is then the test statistic and where that falls. If it falls within this green region or if it falls amongst the two tails. And because we said the t-test statistic that we got in this hypothesis test was 2.37, which is greater than, it's more extreme than our t-critical value of 1.967. That means it's a significant result, and we will reject the null hypothesis. So that is to say, the p-value of 1.8% is less than the alpha value of 0.05. And we can see that here visually because, let's just look here, this test statistic of 2.367, which will be here, is greater than the critical value of 1.967, which means that correspondingly, the p-value of 0.009 will be less than the alpha of 2.5. And because it's a two-sided test, you're going to multiply that by 2, of course. So you're going to say that the p-value of 1.8% is less than a 5% alpha. So that's how you would compare the p-value as it relates to the significance level alpha. So if the p-value is less than the alpha value, you will reject the null hypothesis. It will be a significant result, and you'll conclude with the alpha. If the p-value is greater than the alpha value, that's a non-significant result, and you do not reject the null hypothesis. So that is to say, if the test statistic falls in this green region, you would not reject the null hypothesis. And the reason being is because if it falls within this green region, the p-value, which is the probability of any random variable being more extreme than your test statistic, will be higher than your alpha value of 0.05. So hopefully that helps see how that all gets pieced together. And it usually helps to work with R and try to see things visually in order to get a better understanding of what these different numerical values represent. Does that make a little bit more sense? So the respective commands of finding probabilities, you can either use, you can switch it out. So we learned how to use the normal distribution. You could use the qdist command to find critical values for a given probability. And we can use the reverse. We could find probabilities with a given value. So we could use a given t value to find what the probability is representative of that. So we can use this to find a p-value, for instance. We can use the command pdist. So if we were looking for a t-value of 1 using a sample set with a degrees of freedom of 20, we could find what the corresponding p-value would be by running this command. We see here that the corresponding p-value would be 16.5%. But we could also see if we increase our sample size, this will demonstrate how the t-distribution changes as you change the degrees of freedom. So if we increase the degrees of freedom to 400 and use the same t-value, you could see that the p-value is actually then reduced from, it's reduced now to 15.9%. So it's reduced a little bit. So we can see here how the t-distribution changes as you increase or decrease your degrees of freedom. And then to find our critical values, we can use this command. So this will look at a 95% confidence level to find the critical values for a two-sided test using a sample size of degrees of freedom of 400. So that'll be a sample size of 401. We can run this command and find that the critical values are very close to the normal distribution, which is 1.96. It's a little bit off, but as we said, the t-distribution, as you increase your sample size, it'll become more and more like the normal distribution. But if we decrease it, degrees of freedom, to let's say we decreased it to 15, we could see how those critical values will change correspondingly. So we saw before that we ran this QDist command to find the critical values for a degrees of freedom of 400. It's very close to the z critical values for a normal distribution to get positive negative 1.96. But then if we change the degrees of freedom to 15, we could see how the critical values changed from 1.96 plus minus 1.96 to plus minus 2.13. And that's because the t-distribution will change based on your degrees of freedom. Yeah, so that's right. So if the p-value is less than your alpha value, you reject your null hypothesis. If the p-value is greater than your alpha value, you do not reject the null hypothesis. So hopefully that helps clarify it a little bit.
I think this one's gonna be the same way. I'm over right now. I know. I try to write it. I try to do it like really carefully and like be so concise as I'm writing, and then I'm done. I do everything I feel like I need to.
Did that help make it a little bit more easier to understand? It's good to try to understand what all these different concepts mean, and definitely if it doesn't make sense, be sure to ask for help, because we definitely want to make sure that you understand the concepts behind all of these different
it's just stupid.
All the different components of running hypothesis tests and running statistical analysis.
This should not be the hardest part. Like I wrote the paper in a night, and now I've been spending 2 days just trying to cut it. I was like, I need more policy options. Sorry. No space. Yeah. And they're just like issues with all of them. Yeah, but it sounds like you just have to. What did you say about like policy options? How are you? Just written this paper, living my best life. I also can take those classes, can I? I have a section. Yeah. It's like aggressive. $125 more to go.
Great. Well, I'm glad we were able to clarify that. And if you have any more questions, feel free just to reach out and happy to help clarify anything that didn't make sense.
Well, this is like less. Yeah, that's why.